My name is Joshua Thompson, and I'll be discussing the groundwater pollution from the Fukushima Dai-chi nuclear facility shutdown. So the outline is I'll begin by discussing the basic scientific concept of groundwater contamination. I'll then cover the timeline of the Fukushima shutdown. I'll discuss the geologic setting and two radioactive elements and their relative location close to the nuclear facility. We'll compare this incident to Chernobyl. We'll discuss the societal impacts that this had on the Japanese people. And then we'll cover the remediation efforts that are continuing to this day. So, the basic scientific concept of groundwater contamination. So, the fate of subsurface contamination depends on the local geology, groundwater flow patterns, and much more. Contamination might spread rapidly within a high conductivity sand lens or slowly through clay. When we speak of groundwater contamination, we mean solutes dissolved in the water that can render it unfit for use. The contamination we are speaking of in this discussion is radioactive, and it can render the water unfit for decades or even thousands of years. So the timeline of the Fukushima shutdown is on March 11th, a 9.0 magnitude earthquake strikes off Honshu Island. An hour later, a 46-foot tsunami hits, overflowing the 19-foot seawall, inundating the plant. On March 12th, emergency backup battery for reactor 3 runs out and the fuel rods are exposed. On March 14th, a major explosion in the building for Reactor 3 damages the cooling system for Reactor 2, triggering core damage in that unit. On March 15th, an explosion severely damages Reactor 4, and another explosion takes place in Unit 3. Radiation is measured at the Reactor 3 at 400 millisieverts per hour. On April 12th, the International Nuclear Event Scale level of this incident is raised to 7, and this is the same as Chernobyl. It is determined by nuclear experts to be the most complicated accident of its kind to ever occur. So now groundwater contamination in Fukushima and the surrounding areas. So the geologic setting is that the nuclear plant sits on the alluvial deposits of the Hamadori Belt, a stretch of quaternary sand terraces that extend north to south between the Abu Kama granites to the west and the Pacific Ocean to the east. The facility lies on a coastal terrace at an elevation of about 35 meters above sea level, which was partially lowered to 10 meters to build the reactor facilities. The stratum 1, which you can see on the image to your left, consists of medium grain size sandstones that reach a maximum thickness of 20 meters. The hydraulic conductivity of the unit is estimated to range from 2 to 4 times 10 to the negative 3 centimeters per second. The underlying unit, or stratum 2, is constituted by the intercalation of silts and mudstones with a thickness in the order of 5 to 7 meters. Both stratum 2 and 3 provide the foundation for the reactors and the buildings at the facility. The precipitation is on the order of 1,550 millimeters per year, and considering that the evaporation reaches about 700 millimeters per year, the aquifer would receive about 540 millimeters of recharge from rainfall alone. And this is really important for the groundwater discussion later. The bulk of the groundwater currently flows through the sandy layers of the stratum 3. And this unit constitutes thus a leaky aquifer fed both from upper units as well as by inflows from the western margins of the premises. And so even when most of the radionuclide concentrations in groundwater were measured near the surface, anomalous levels of tritium were detected up to 30 meters below the base of the reactors. This suggests a high degree of hydraulic connectivity between shallow units. And so, looking at the spatial distribution a year after the incident of tritium, and so the spatial distribution of tritium concentrations was clearly discernible, and higher tritium concentrations were measured at wells nearer to the facility as well as shallower depths, which you can see on the left, on the two graphs on your left. And the tritium was considered to have been released to the atmosphere as tritiated water vapor and scavenged from the atmosphere as precipitation. So if you look at figure 3 on your right, the closer you are to the facility, which is the boxed in region on the top right, the closer you are to the nuclear facility, the higher concentration of tritium. The farther you move away, the less the concentration of tritium becomes. And so this is in 3 cities near the Fukushima facility. And so the groundwater levels observed, and so on the left is a borehole analysis of the groundwater. So the groundwater level observed in the deeper borehole was higher than the groundwater level in the shallower borehole throughout the observation period of mid-July to mid-August at Kutashi. Therefore, an upward hydraulic gradient was dominant around the borehole at Kutashi, and this suggests that the site is a discharge area of the groundwater flow system. In contrast, the hydraulic gradient in the borehole at Ibuyashi was downward, which suggests that Ibuyashi is a recharge area for the groundwater flow system. And so the driver of the groundwater contamination in the areas around the nuclear facility are precipitation events that carry the atmospheric concentrations of the radioactive elements. And so on the right are river discharges, and you can compare this to the left to determine what I had previously discussed. So kind of comparing Fukushima versus Chernobyl. So according to the International Atomic Energy Agency, there was less total atmospheric release of radioactivity from the Fukushima accident compared with Chernobyl, and this is due to the different accident scenarios and mechanisms of radioactive release. In Chernobyl, the release started with the nuclear criticality accident, and this triggered an in-core steam explosion, causing an intensive ejection of the overheated core material and extensive burning of graphite, which was located inside the facilities and reactor materials over a long period of time. The release was not confined because that type of reactor did not have a containment unit such as we have today. As a result, radioactivity had a direct open path to the environment, enhanced by the entrainment in the smoke from the burning graphite. However, the Tokyo Electric Company, which ran the nuclear facility, dumped gallons of radioactive material into the ocean. And this is where the radioactive material was found its way to California via ocean currents. And so radioactive particles from the Fukushima nuclear disaster are being found in local wines in the Napa Valley. Since more data has been collected on Chernobyl relative to Fukushima Dai-chi, it remains inconclusive which nuclear disaster is worse, but one could predict that Chernobyl was worse because of the direct influx of radioactive material into the atmosphere. Societal impacts. So there are many societal repercussions from a nuclear disaster. These can be seen in the image on the right. The main effects, though, of the groundwater contamination, they are affecting fishermen. Due to the large amounts of nuclear radioactive waste dumped into the Pacific Ocean, the fish contain high levels or higher levels of radiation. In addition, bioconcentration exacerbates the situation. Algae become contaminated and then affect the rest of the food chain, including humans. Reports of contaminated drinking water are also a concern as the groundwater is contaminated by the nuclear facility as well. Contamination and decommission of the Fukushima facility rely on three basic policies: to remove and treat existing contamination, to isolate fresh waters from the contamination source, and to prevent leakage of contaminated water. The problem of groundwater contamination of Fukushima starts in the Abukama Mountains. It is estimated that 400 cubic meters per day of fresh groundwater flows from the peaks overlooking the complex towards the reactor halls, where it mixes with the contaminated waters generated from cooling operations. Contaminated water is pumped out and temporarily stored on site in approximately 900 tanks, each holding a maximum of 1,000 cubic meters. In effect, the tanks have a finite lifespan, while the spills and leakage incidents are an ongoing problem. And cracks in the reactor foundations, combined with potentially inefficient methods for collecting cooling water, most certainly lead to direct radionuclide inputs to the local aquifer and subsequent transport to the coastal ocean via submarine groundwater discharge. In this regard, the seaside impervious wall constitutes a fundamental measure to block the flow of contaminated water into the ocean, which you can see an image of this on the top right. A second impervious barrier, informally known as the ice wall, is being constructed around the reactors to intercept groundwater fluxes to and from the buildings. Artificial ground freezing appeared 150 years ago in the coal mines of South Wales and is particularly widespread in civil and mining engineering, as well as for the containment of hazardous waste in environmental projects. A successful test was initially carried out in March 2014, opening the way for a large-scale design which is scheduled to be used until 2020. The ice wall prevents groundwater from the uplands from reaching the basement of the reactors where radioactive water is accumulated. At the same time, a restricted groundwater inflow translates into a gradual decline of water levels and the consequent reversal of hydraulic gradients inside the walls. Inflows into the reactors are being further reduced by pumping groundwater out on the mountainside of the power plant. And then the flat lands and the slopes around the nuclear plant are being covered with an asphalt layer or facings that restrict rainfall recharge and contribute to a general reduction of the water table. The ultimate purpose of the strategy is to minimize seepage and prevent thus any rainwater from being mixed with the contamination plume. So in conclusion, rainfall events are the drivers of the groundwater and river contamination. The elevation gradient drives local groundwaters to the ocean and reactor basements. And the societal impacts from specifically the groundwater contamination are the fishermen because of point 2 in this, and local drinking waters are also being affected. And so there are various remediation efforts that are ongoing to this day, and there's still more that needs to be done.